when you make nuts, you turn the tap and you thread it, and you get a nut. But then you have to reverse the tap to take off the nut. So, of course, that slows down production. So everybody was looking for a way, can you take off the nut without stopping and without reversing? So you say, well, how can you? You have to connect a chuck to this and drive it. You add more and more nuts, they'll accumulate, and then what? So is there a way to get the nut off the shaft without stopping the shaft rotating? When you say that this can be done or cannot be done because it violates physics, you really have to be good at physics to know does it really violate it. And that's the catch. The catch is you have to understand each law very well to say, just a minute, it doesn't apply to me. If you don't think about something when you shower, you're not in the right field. Because the stuff that interests you is the stuff you think about at the shower. And that's the stuff you should pursue. Because your brain is working on it 24 hours a day, not just 8.
In this episode, Mike and Misha sit down with Dan Gelbart, legendary engineer and prolific inventor. From the first working laser to so-called impossible machines, Dan shares some pieces from his personal collection that reshaped our understanding of the limits of physics. He explains the stories behind some of his most successful inventions, what decades of hands-on engineering taught him about skepticism, and how creativity and clever thinking can create technologies that change the world. Please welcome Dan Gelbart.
Cool. So this is the first laser in the world which worked. Now actually, Ted Maiman had a laser and a spare. The housing is actually the spare. His widow, Kathleen Maiman, who lives in Vancouver, she has the original housing, and the ruby is from the first laser. You can tell because in the first laser, the mirror was hollowed out in the middle to give 1% transmittance. And the big innovation in this laser compared to what people tried to build, which didn't work, is Ted Maiman went against common wisdom of that time. Everybody was trying to make a gas laser, which is a continuous lasing, a CW laser. And Ted Maiman said it was much more chance to make a pulse laser because you don't have to worry about thermal distortion. It just pulses quickly, and then it can cool down. And then he realized you're much better off making a solid-state laser instead of a gas laser because you can make it very short because the density of atoms is so much higher, so you have enough atoms in a small space, and because it's small, it's easy to keep the faces parallel. It's just a crystal, you can lap it parallel. And the third thing which went against the grain, it was assumed at the time that ruby doesn't have enough gain to laze. So this population inversion, the principle of a laser, just wouldn't give you enough performance in ruby. So Ted Maiman did his PhD on ruby. He made a ruby maser, and he somehow didn't believe that common wisdom, which was expressed in many articles, that the ruby cannot laze. So he asked his technician to remeasure the ruby gain to see if it can laze, and his technician came back and said, Dr. Maiman, they're right, I measured it, and it's just like they say, it doesn't have enough gain to be a laser. And Ted Maiman didn't trust his own technician, and he went and measured it himself, and then he realized everybody was measuring it wrong. So all the reported results, including from his own technician, were wrong. And when he measured it the right way, it showed that it has a huge gain, and it's one of the best materials.
Do you know what the difference was between the measurements?
Oh, I don't know. He explained in his book, but I don't remember.
And you have the notes, right?
Yeah. But basically, he understood that people didn't understand how to measure it correctly. So then once he measured the ruby correctly, he realized that ruby is an excellent material for a laser. And indeed, this laser I'm holding in my hands worked on the first try. And I have a page from his notebook. If you pass on, this is from May 16, 1960. And that is the first time the laser worked. And you can see this picture, which is a laser. And there is a photocell connected to a scope, where it says memoscope, and there's a capacitor. He discharges into the flashlight, and he watches the intensity at the right wavelengths. because there was glow from the flash lamp. So there is a filter here looking for the right red light that he expected. And as he increases the charge on the capacitor, the energy at the right wavelengths goes up and up. But that's simply fluorescence, because the ruby also fluoresces at these wavelengths. But at some point, it jumps up a lot. There is a knee in the curve. And he put a question mark here, is that the threshold of lasing, which it was. So this is the first time anything lased.
Amazing.
Okay?
I think it's also interesting how he measured the power.
Well, the power is just measured with a photocell. And he just
Was it
measured...
photocell? You said that number of blades it could...
Oh, no.
Right.
Later on, they wanted some
High
method
power.
that labs can compare nodes. So they used razor blades. So how many razor blades a laser can drill in one pulse? And that used to be the unit of pulse laser power. It was called a razor blade, like a 10 razor blade laser, 5 razor blade laser, because they didn't have power meters at the time which could respond to a microsecond pulse or even a millisecond pulse, right? Because nobody needed such power meters. So they all went by, they put a lens in front of it, focused the spot, and counted how many razor blades it can drill.
It's for the peak power.
Because it's the peak power here is many kilowatts. Because a flash lamp discharging has a high peak power. So this laser already in the first try could drill a couple of razor blades. And then very shortly, the rubies, everything was improved that it could drill many razor blades in one pulse. And later on, of course, they had proper power meters.
Do we still use this ruby lasers?
Okay, so today, the lasers today are very similar, but instead of ruby, they use YAG. Because the YAG material has more gains than ruby, but ruby is still a very good material. Okay, so the YAG is a bit better. It's also different wavelengths. The YAG is infrared, usually 1065 nanometer. But rubies, if there was no YAG in the world, all the lasers will still be ruby and they will work fine. So it's amazing that everybody in the world was convinced that ruby cannot laze, and Maiman had total faith that not only it can laze, but it's one of the best materials.
Did you meet with him?
He was a friend of mine until he died.
I see.
That's how I ended up with this. Because he moved to Vancouver. The last 10, 15 years he spent in Vancouver and we became friends.
There must be something magic in Vancouver that people like.
One lecture you have on YouTube, which I thought was fascinating, was this lecture of like impossible problems that turn out to be solvable.
Yes.
Basically examples. If you can, maybe you can just go through those, because I thought the lecture was incredible. It was kind of poorly recorded. So I think to record another version here would be really interesting.
So, okay. So one of the subjects was to tell people how to estimate the difficulty of a problem. So if somebody approaches you with a problem and, it's good to have an idea. How difficult would it be to solve? That's very practical skill, because if you want to come out with new technology, you always want to be on the edge of what's possible, because if it's easily possible, other people will do it, right? If you misjudge and it's a bit beyond the edge, you will waste a lot of money and fail. So it's important to be able to judge where is the edge of technology, where other people think it's not doable, but you believe it's doable. And that's how you can make money, because you concentrate on that. But you have to be very good at judging where the cliff is, that you are on the right side of the cliff. Okay? But for that, you have to learn to estimate what's doable, what's not. And there is a lot of things which people thought was not doable at all, and then turns out it's easy. And a lot of things people think they could do within a few years, and they're still working on it 50 years later with no progress. So people made a mistake both directions. Okay, so I think the basic rule is if it doesn't violate any law of physics, it should be doable. So the only thing left is how long will it take to do it? And there's another thing you have to understand. Is there a loophole? Maybe it appears to violate the laws of physics, but it doesn't, because there's a loophole. In this application, it doesn't. Okay, so I'll give you an example. There is somebody by the name of Earnshaw proved many 100 years ago, more than 100 years ago, that you cannot suspend magnetically an object in space passively, not with servo systems. Basically, what Earnshaw proved that if you have a bunch of magnets, no matter how you position them, you cannot make an object float in space above the magnets. And that's a fundamental thing. It's actually true not just for magnetic fields, it's true for any field where the force is the square law, 1/square law of distance or higher. Okay? So it's actually a very fundamental principle for all square law fields or higher. And people tried a lot because they tried it for practical reasons, like maglev trains or ideas, bearings with no friction. And they all came to the conclusion Earnshaw was right. Okay, you can't. But you can always think, is there a loophole that in my case it doesn't apply? So, for example, if you take this, you can suspend it magnetically if one degree of freedom is limited. So basically, this doesn't violate Earnshaw's law because the object seems to be suspended, but it's blocked for one direction. So it doesn't have all degrees of freedom.
What happens if you remove that?
It will snap.
Can you remove it or not?
Yeah, it should be able to. There's no way, no matter what you do, you'll never be able to suspend it.
Okay.
Because that's Earnshaw's law. If you could do that, you would violate Earnshaw's law. Right? Earnshaw's law says, okay, so one way out is saying, okay, Earnshaw's law doesn't apply because 1 degree of freedom is restricted. Okay. Another way to get around Earnshaw's law, if you spin it, if I spin it fast, it turns out I don't need this. Because the force which tries to collapse it flips back and forth too fast to do anything. And this is the spinners, magnetic spinners, which spin in the air when you spin them above a magnet.
Is that the spinner?
No, that's not. I don't have one of those spinners, but you saw them probably in videos. And the reason it doesn't defy Earnshaw's law, because it tries to flip over, but it spins so fast that the flipping force reverses. So it's another loophole. So even if you say this will never work because of Earnshaw's law, you shouldn't give up. You should say, maybe it doesn't apply to my specific case because I'm spinning the magnet, okay? Here is another example of getting around Earnshaw's law. I have an array of magnets here, and I have a piece of conductor, and I put it above the magnets, and you can see, I just move away.
Do you magnetize it, essentially?
No, watch. This piece is floating.
Floating, yeah.
You can see it's floating because it's kind of going back and forth. Okay? I can put it a bit closer to the camera. It'll be easier to see it floating. Now, this is really hair-raising.
Did you do the same with the like YBCO superconductor?
Okay, so everybody who's a physicist looks at it and says, obviously, that's a superconductor.
No.
But it's room temperature.
Yeah.
Now, if I had a room temperature superconductor, I would be lecturing now to the Nobel Committee in Stockholm, not to you. So obviously, it's not a superconductor. But it floats like a superconductor against Earnshaw's law. Okay? So it turns out that this is diamagnetism. Because there are ferromagnetic materials which get pulled to the magnet, but there's also diamagnetic materials which are repelled from a magnet.
And superconductor is diamagnetic.
Superconductor is diamagnetic, but
diamagnetic
you don't
material.
have to be a superconductor. Like a regular graphite is diamagnetic enough to float.
To float, I see.
But then it bypasses Earnshaw's law, because Earnshaw's law is only for attraction, square law attraction. It doesn't apply to repulsion. So here is a very simple way to get around Earnshaw's law. So anyway, this is just an introduction to say, don't give up too quickly. You know, the Earnshaw's law says you cannot float something, but I just showed you 3 ways to do it. Okay, and that's true for many, many devices, that you shouldn't be too much in a rush to say, oh, it defies this law of physics, forget it. You always have to think, maybe there's a loophole. And I'll show you a few examples.
It's like hacking the reality.
Exactly. But when you say that this can be done or cannot be done because it violates physics, you really have to be good at physics to know does it really violate it. And that's the catch. The catch is you have to understand each law very well to say, just a minute, it doesn't apply to me. It's just like a good lawyer in a trial. He has to find a loophole. Okay, so I'm going to show you another example. When you make nuts, you have a tap and you have a nut, and you thread it. You tear the tap and you thread it, and you get a nut. But then you have to reverse the tap to take off the nut. So, of course, that slows down production, because any machine which has to reverse has to stop and reverse. So everybody was looking for a way, can you take off the nut without stopping and without reversing? So you say, well, how can you? You have to connect a chuck to this and drive it. You add more and more nuts, they'll accumulate, and then what? Okay, so is there a way to get the nut off the shaft without stopping the shaft rotating? So again, you look at it and it says, no way, because this has to transmit a lot of torque to tap. So it has to be physically held. And what do you do? As long as it keeps turning, the nuts climb up and jam. But then it turns out the solution is trivial. All what you have to do is have a tap which is bent. So instead of a straight tap, you make a bent tap. And it's the same tap. The bottom is tapping and the nuts climb. But because it's bent and you put it in a bent channel, you can transmit torque. See, now you can turn it and you can transmit torque, and as the nuts climb up, they can fly out. Okay, so it taps and as the nuts climb up and fly out through the hole, and you don't have to stop and reverse. So again, this made an amazing difference in the speed you can make nuts, and it's such a simple idea. Okay? So anyway, there's many ideas like this, and all the examples is to tell people, don't rush to say possible or not possible.
What's if you had to think about like some interesting kind of not principles, but like, so this is, for example, like this is adding like another axis, basically.
Yes.
Right? So this is like finding a topological kind of like trick.
Yeah, and there's many ideas based on topological tricks.
Yeah, so that's one area is like, can I add a degree of freedom
another
or like
dimension.
Another dimension?
And that helps in a lot of cases.
What's another style of like loophole?
Well, again, each one is very different. I couldn't formulate a law which saying this is the way to find loopholes, right? Because in each field, the loophole is different. For example, there was a guy, I remember, his name was Jack Rabinoff, who had to make a mail sorting machine, and the machine had to pick up very fast pieces of mail and move them over. But he had a problem because it was pulling with a vacuum, and the vacuum wasn't strong enough. Say if you had a parcel and you had a small nozzle to pick it up, it can only pick up 1 kilo per square centimeter, and wasn't enough to. And then people said, well, that's it. If you want to pick up with vacuum and you only have a small nozzle so it can pick up little things, there is a limit on the force. The limit is atmospheric pressure. And he said, no. I can enclose the whole machine in a steel box and pressurize the air in that steel box to 2 atmospheres. And now I have 3 atmospheres, right? Because I have 0 or minus 1 atmosphere in the vacuum plus 2 atmospheres of gas in the room. So I can actually put any force I want on the vacuum system by pressurizing the room. So that's kind of an idea, just an example of thinking a different way.
Yeah.
Okay. One of the amazing examples of thinking a different way is this electromagnet. So this is an electromagnet which, like any other electromagnet, picks up steel. Okay. I have a piece of steel, but it also picks up aluminum and copper and any non-ferrous metal. Okay, and there's no cheating here. That's actually copper and aluminum, and it picks up aluminum, picks up.
Well, what was the diamagnetic also sample?
What's that?
That the diamagnet will all.
Well, the diamagnetic it probably wouldn't pick up unless it's conductive enough. But it has to be conductive. Let's see. It may or may not, depending on the conductivity.
Make your bets.
No, it doesn't pick it up. It's not conductive.
Okay. Makes sense.
So the key you could already see is that the material is conductive. Like it wouldn't pick up paper, wouldn't pick up wood, wouldn't pick up graphite, but it picks up any conductive metal. It doesn't have to be ferromagnetic. And that, to me, when I read about it in some old book, it blew my mind that you can make such an electromagnet. Okay? And again, it shows you don't rush to say possible or not possible. So the way this works is a really devious way. If you have a rotating field, it will drag a piece of metal with a rotating field, just like an induction motor works, because the rotating field will induce a current, like an eddy current, and that current will create its own magnetic field, and the interaction between this magnetic field and the magnetic field induced at this piece will create a force, exactly like induction motor works. So if I had a rotating field and I put this piece of copper in a rotating field, the copper will start rotating with the field, because if it didn't rotate, it will have a huge induced eddy current, which will cause a magnetic field, which will cause a force. And only when it tracks the field, it sees no flux change and there is no eddy current. Okay, so exactly the principle of induction motor. So what this is two rotating fields, one going this way and one going this way. So when you put something in, it tries to follow one rotating field this way or follow the other rotating field this way, but in both cases, it's actually pulled in because it wants actually to rotate, but it's stopped by this. So basically, you have to make here two coils, like the coils of an induction motor. And the way you do it from one phase, the way you make a rotating field from one phase, is you can shift the phase because you need two vectors shifted. Doesn't matter what angle. So this is shifted with a piece of shorting ring, just like if you take a electromagnet and you cut and put a copper ring, it shifts the magnetic flux. So now you have two phases of flux, and then if you have two phases, you get a rotating field. Okay, so the two fluxes make a rotating field, and the rotating field is trying to make everything rotate like this, but when it hits this, it can.
And then it uses current, right?
Yeah. So any conductive material will be attracted. So, but if you don't understand the theory, to you it looks it just attracts any metal, not just steel. Okay. So again, if somebody asks you, could you make an electromagnet which will attract a copper, aluminum, you say, no, electromagnet will actually repel it. If it works on AC, because of Lenz's law, it will actually repel aluminum and copper, not attract. Because this side is a conventional pole. So if I put the aluminum on this side, which is a normal electromagnet, it will repel it. See, it's pushing it away. And if I put copper on this side, it will repel it. Okay? But if I put it on this side, because of the two rotating fields, it pulls it into the pole. That's a bit of a more complicated explanation, but the result is totally counterintuitive, because the same electromagnet on one side repels copper and the other side attracts copper. Because one side is a conventional AC electromagnet, which repels the copper by Lenz's law, and the other side is two rotating field, which is really an induction motor, which makes it rotate inwards. So anyway, that's kind of a good example that you shouldn't say no too quickly.
So what are the problems which are easy but then difficult to solve?
Oh,
impossible?
There were many of those that people misjudged how long it will take to solve by $100 billion in 50 years, like fusion. When people started working on fusion, they're always 10 years away, because people said, look, if a bomb was made, a fusion H-bomb was made, obviously fusion works. You can demonstrate fusion with explosives very easily. And there is a tabletop demonstrator for fusion made by Farnsworth almost 100 years ago. The guy who invented the electronic TV. Farnsworth, he retired later on because RCA pushed him out of business. And he was a very clever guy, self-taught. And he invented this scanning of electronic television. Before the television had a rotating disc, a mechanical scan. And he invented electronic scan. But anyway, he was a bad businessman. Sarnoff was a very smart businessman. made his life miserable, pushed him. So he retired to a small village where he grew up, and being bored, he thought what to do, and he invented the only desktop fusion device which is still used for teaching. You just plug it in and it does fusion. But it doesn't do positive energy gain.
Exactly. Yeah.
So 100 years ago, almost 100 years ago, there was already a tabletop device which could do fusion. And later on, there was a fusion bomb, and you can do fusion with explosives. And people said, so why don't we just build a fusion plant? Obviously, it works. It works on a desktop scale. It works on a bomb scale. So it will work on any scale in between. And 8 years later, still no fusion, which is positive energy gain.
So what do you think? What's the main challenge?
I'm no fusion expert, but I'm saying that this is something mankind misjudged by 80 years and endless amount of money, and there's still no answer. And there's many, many stories like this.
So you love precision, right?
Oh, yeah,
And
that's hobby, yeah.
One of the most famous precise instruments now is the ASML stepper.
Oh, yeah.
Right? Which is now being sold, for $300 million and so on. And it's kind of considered like that nobody can make one besides ASML and so on.
And the Chinese are desperate to make one and failing.
Have you been tempted to make a stepper?
The thing is, in order to make one, you have to believe you have a better idea than others. And I don't have the knowledge to even know if I will have a better idea. You have to spend time and understand it because it's immensely complicated technology. I mentioned before that I worked on this nonlinear thermoresist, which I thought could be the basis of a higher resolution stepper. And we did develop, together with the university here in town, a very good thermal resist. And we modeled it and tested it. But
so it's a resist which when you heat it with
change solubility, yes. It's a photoresist, but thermally activated, which is totally nonlinear. So that part is very good. But with today's geometries, you run into the basic optics problem. So basically, first, there is two ideas. One idea to approach it from making the ideal resist that has no crosstalk, no proximity effect. And you can achieve that with special ideas and resist. But you still don't get around the problem, how do you bring the wavelengths down so much so that you can write nanometer lines? And as you know, in the ASML current machine, a huge part of the money was to develop the EUV source, which is...
And the optics.
Well, the optics are mirrors, but the problem was to make them so perfect.
Exactly.
There is a very good video by Veritasium, and that's which shows the difficulty, gives you the idea of the difficulty. I visited ASML many years ago, but most people don't understand why did ASML succeed where everybody failed, including China, which put in billions into this effort. And ASML succeeded where everybody failed because they went against common wisdom in manufacturing. Because common wisdom is always never rely on a single source. Because that single source lets you down, you're stuck. So everybody was taught if you manufacture, you have to have multiple sources for each part. The usual story. ASML said, no, this is not the way to succeed. The way to succeed is find the best supplier in the world for each component, each critical component, and make an exclusivity deal with them that they can only make it for you and you can never buy this part for somebody else. So ASML looked around and said, who is the company which makes the best lenses and optics in the world? And that was clearly Zeiss. Carl Zeiss in Germany, they had a long tradition. And they went to Zeiss and says, you will make us the lenses and we'll never buy lenses for somebody else, but you cannot sell the lenses to anybody. And they signed a deal, a multi-year deal. And the lenses changed. Original lenses were for 193 nanometer. Now they are mirrors for EUV, but they stayed with the same supplier. Then they thought, who is the best metrology place in the world? And there was a group at Philips in Eindhoven. And Philips is known for light bulbs and refrigerators and appliances, but Philips had a phenomenally good metrology group. And they went to Philips and says, we want to make a deal with your metrology group. We don't care what you do with the rest of your products, but they will only work for us and we will not buy from anybody else. And they did more than that. They said, we will guarantee the profitability of each one of these suppliers.
It's like a cumulative effect, seems
Yes,
like.
so-
So for China, it seems like
Ye-
in order
okay,
to make it, they need on
okay.
every single step.
So that's a barrier that ASML locked up the best vendor in the world for each component. There was a company which made the excimer lasers, so ASML bought them, Cymer. So some companies they bought and some they made this deal. So at the end, they ended up that for every critical part of the machine, they locked up the best vendor in the world who couldn't sell to anybody else. Okay, and that's why nobody can compete with ASML. Because to succeed, you'll have to find a replacement for Zeiss, a replacement for Philips, a replacement for Cymer, a replacement for 10 other critical vendors.
It's like whole world efforts.
Exactly. And that's why the Chinese, that's one of the few things they miserably failed. And they gave up and now they started again. You know that. They had a lithography project for 10 years which failed. And now they started again to make an ASML-like machine. And it seems they got very little progress. They managed to make the source part. And it's not as good as ASML after spending a huge amount.
Why it takes time to get to this level of precision?
Trade
Can it be accelerated?
secrets, there is experience of people, there is trade secrets. It's not something you can look up in a book.
Yeah.
Especially when you have to polish a mirror flat to one atom.
Mm-hmm.
Okay, there's always some old guys there who know what to do and these are irreplaceable, right? So that's an amazing story. And what is so amazing about ASML is their philosophy, that they have single source for everything, the best in the world, and that's a barrier.
That's super interesting. I don't think I've heard that analysis.
Oh, yeah. No, that's how they operate. Yeah, as I said, I visited them and I know them well.
The best bolts, the best nuts, the best mirrors, it starts from
No, bolts or
simple
nuts, somebody else can also make a good
Sure,
enough
yeah.
nut. But if you look at some
the
key
critical
elements,
components.
like the mirrors, the motions, the lasers, there's about 10 critical elements. If you lock those up, it'd be very, very difficult, especially Zeiss with the lenses and the mirrors. Because Zeiss, it's a very long tradition of how to make these optical parts.
Yeah, I feel like I can understand, switching the fields, like when you go to high precision, it's like a completely different universe. Like you need to take everything into account.
That's true. And there's a lot of materials knowledge.
Like details you don't take usually.
And there is a lot of experience of older people who've been doing it for many years.
Yeah, exactly.
That's why I mentioned before in this factory where they make the jig borers, in that book, everybody looks older than I am. Because these are people who've been doing it 50 years, same job. And you just don't understand how they can do it so fast. Because, they scrape the thing to submicron in minutes. And you try it takes you days and it's still no good. Because, if you've been doing the same thing 50 years, you can do it with your eyes closed to perfection.
So do you think that maybe now there's like a big bet on AI kind of pushing the limits on maybe high precision, like something which people didn't realize, but by trial and error, see like some trends, solutions?
Most people don't make the connection between metrology, this high precision, and computing power. Because the limit to computing power is metrology.
Sure.
Because if you can make denser chips, you can compute a lot faster, and the chips take less power because the gates are smaller. If the gate is much smaller, it takes less power per gate. Mm-hmm. So you can put more gates on the chip because they dissipate less power. So what limits computing power is the metrology of the stages and the metrology of the optics. And both optics and the positioning, it's a mechanical limit. How accurate can you make a mechanical part? In the case of the mirrors, is how you have a shape, parabolic shape.
Yep.
How accurate can you make this parabola? It's a mechanical problem. And the motion of the stages is you have to move these stages to nanometers. So basically, if you had 10 times better metrology, you can make computers 10 times more powerful.
But could it work in the reverse way? Like, let's say if it's, let's say for optics, we are not limited by just spherical surfaces. If we go to spherics or more complex patterns,
you still
and which
need
is
the
kind of
accuracy.
beyond the...
No, you can have new ideas there, but you still need the brute force accuracy.
Sure.
Because if you make an aspheric lens, it's even harder.
Yes.
Because a
Much
spherical shape is self-generating. Self-generating means if you rub two pieces of glass together, they'll become spherical.
Yes.
But if you wanted aspheric, it's much harder, but it's not self-generating. There is no averaging effect. So spherical is actually self-generating, and it relies on averaging, like lapping. Any lapping relies on averaging, okay, and self-correction. But aspheric is not self-generating. If you rub two pieces of glass together, they'll never become a spheric, the shape you want. They'll only become spherical, okay? So because of that, it doesn't help. You can compute better. You can model the lens much better with computers, but you still have to make it to atomic tolerances.
Well, I mean, like for the tools, let's say you will have a control of how you
So this is
manufacture it.
okay.
and
So this is a common
dynamic
fallacy.
adjustments.
Okay, this is a common fallacy for most people who didn't work in this field. Most people who didn't work in this field says, why do we need this crazy precision? Why don't we close the loop and measure the error and do closed loop control and fix it?
The idea, right?
Yeah, the way you take out distortion from an audio amplifier. You close the loop and take out the distortion. So it turns out you can't in metrology, because it turns out that the same reasons which limit the accuracy in first place will prevent you from closing the loop. For example, you can calibrate the system to try to take out the errors with a lookup table, but the system will drift, and the calibration will drift, because it will wear. If something is not perfect, it will wear at the high spots, and it loses its accuracy. So it turns out that using this adaptive or software or feedback or even all kinds of clever feedback, not just normal feedback, but predictive feedback of high order, you can improve the performance 5x, 10x, but you cannot take something totally bad and add infinite power and make it good.
10x would be great. I mean, that's like already
10x is about the limit. So all these systems use corrective tables. So when I say Philips makes these perfect stages, they still correct them with lookup tables.
Sure.
Okay, but the starting stage has to be astonishingly good that you can improve it a bit with some lookup tables at the end. Okay, and yeah, it does use feedback. All these ASML machines, they use a lot of sensors and feedback, but the basic system, say if you have a parabola, which is not perfect parabola, there is no software correction for that because it's loss of information. The way to understand it best is think of a low-pass filter. If you have an electronics low-pass filter and you send information through it, you lose some of the information. There's nothing you can do after that low-pass filter to restore what you lost. And that's basically what Shannon came up with, saying you have a bandwidth, there's only so much information you can pass through this channel, nothing will help you. You can code and code, but to reach that Shannon limit, no more information can be transferred to the channel. Now, the same is true for optics. The information meaning the sharpness of the image. Okay, if you have some bad optics and you get some bad image, there is some tricks you can recover some of the aberrations. But basically, information is lost. And that information lost cannot be recovered by any tricks. So if the parabolic mirror in an ASML machine is not the perfect parabola, there will be some blur, and that's it. Instead of a sharp edge, you get a soft edge to the line. There's nothing you can do which will help you. So there is a fundamental limit. However, if the line is very sharp and accurate, software can position it if there is some small error, and you have also a problem with aligning the different layers in a chip. And this can be done by feedback. You sense the position and align it.
Good moment to ask, like, just a brief history So how did you end up here? What's your like brief just life history? Just to give some background.
I was born actually in a DP camp after the war. My parents were Jewish. So I was born, they were in the Holocaust. I was born in a DP camp in Germany.
Mm-hmm.
And then my parents moved, ended up in Israel. And then I ended up in Vancouver in about 73.
How old were you when you came here?
26 or something like this.
Was this after undergrad, or did you already go through after the army? Something like that?
Yeah, I served in the army, of course, in Israel. I was an officer in the army, to show you that even the Israeli army makes mistakes. And I had a chance even to be an infantry soldier in the Six-Day War.
Oh, wow.
And after that, I came here looking for peace, mainly peace and quiet. So I remembered looking at the isotherms on the globe. In those days, there was no internet. So that was early 67. So I looked at the isotherms on the globe, looking for a English-speaking country which has no draft and not cold, because Israel was a nice and warm place. I was afraid of the cold.
And America at the time was fighting in Vietnam.
Yeah, so U.S. was out because I wasn't, if I didn't want to go to U.S. So basically there was New Zealand, Australia, and Canada, which were English-speaking, no draft, sitting on an isotherm which looked good.
What about UK?
What's that?
UK?
Well, UK is cold.
Oh, too cold.
Yeah,
I'm just comparing Vancouver because it feels like Canada is...
No, I didn't at the time. Anyway, I didn't know anything about any of the places because I was never outside Israel. But then I heard about these two Australians who moved to Vancouver. And I said, maybe they know something I should know. So I decided if they move to Vancouver, I'm coming to Vancouver. I really didn't know much. And I wrote a letter to the Canadian Embassy if they can send me some information about Vancouver. Again, pre-internet days. And the only stuff they had was brochures for European tourists, which emphasized the wilderness. So they sent me this brochure, and I had no money, of course. They sent me this brochure about the great wilderness here, and I remember it said that you can walk for days in the forest without seeing a human being. So it scared me. So I phoned the embassy, and I said, how many people live here in Vancouver? I didn't know anything about it. And they said 1 million people in Greater Vancouver, so I relaxed. I said, if 1 million people can make a living, I can make one more can make a living. So I decided to come here. And I mean, I had actually a wonderful childhood in Israel. It was an absolutely great place to grow up. But mainly as a political situation I didn't like.
Where did you get your initial engineering training?
Oh, I was one of those people who knew from age 5 what they want to do.
Mm-hmm.
So I always built stuff. And then I went to the Technion in Israel, which is a very good school. And then in the army, except for the Six-Day War and some courses in infantry, I spent most of the time in a lab. So building spy equipment. So I had some training in the army. So actually I had a very simple life. But most of the training is self-taught, just from interest. I always had a workshop, I always built stuff.
How did you do self-taught? How did you teach yourself things before the internet? I think that's probably like a lost part. Like where does information come? Books.
Actually,
but how do you even know which books to buy?
You're much better off without the internet to teach yourself, because because the internet is just like short tidbits and not kind of a serious in-depth training.
But how do you know which books? For example, when I look for textbooks, I'm like Googling or reading on the internet.
I had the advantage that I had lots of time, so I just read all of them.
Okay.
Because there was a very good American library in Israel. The US put up free libraries in many countries. And there was a great American library in Israel, and you could take as many books as you want, and so I just went to the technology section and read all the books.
So what's your favorite book?
Well, there's many books, and then in the Technion they also had a great library, And in general, I didn't go to the lectures. I just spent time in the library and sat home reading books. So you develop the feel. You develop the feel which books are good. Like if I have to advise young people if they want to learn a new field, unless it's very new, I always tell them look for books before 1965, preferably British books. Because in Britain, there are these people with this esoteric expertise which write like a book about a very narrow subject and endless details. So these are the best books from my experience. So after a while, I knew how to recognize like a good book. You know, it had to be old. The author usually had a hyphenated name, like Sir, this and that hyphenated. So I had all the good sides of a good book, lots of pictures. So you develop the feel for the right book, and then if you read a few books which are less good, there's no harm done. The internet is actually not a great place to learn in depth because, of course, everything is made to grab attention.
But do you think it's like, because first I feel like from the internet you want to just get like some idea and then you maybe got into like solving the problem and then you see like the details and then it becomes meaningful because...
So the internet is great, and especially now with AI, that the AI can summarize for you what's known about a field and give you links to read in depth. So that's good. But if you want to learn a subject in depth, you're much better off from a good old book than from the internet because of the nature of the internet. You know, if somebody will put a very serious lecture on the internet and in details going through things, nobody will watch it because of short attention span, and it will also not get a high rating. So the internet algorithms will never suggest it to you. Because when you look on the internet, say, YouTube suggests to you similar videos. But if that video is like a serious lecture, it will never be suggested because it has very few views. So, right, it will suggest some popular stuff with higher views. So it's basically, it was just as easy to learn before the internet as with the internet.
And you have a YouTube channel and you also teach students, right? What's your approaches? How do you do that?
Fundamentals, dwelling on fundamentals, because the current method of teaching has a problem that there is no retention. See, when you have a company, you don't measure the input. You have a company, people only want to know the output, say the profit. They don't care how much material you buy. They don't care what's the input. They just want to see the results. Now, the only result of academia should be retention. When you graduate, how much do you know? Nobody measures retention in academia. They only measure input. Which courses did you pass? Which exams did you pass? But nobody measures, do you actually remember a single word of all the stuff you learned?
How many papers you publish, probably?
But
grad school.
But the strange thing is, to my knowledge, no university tracks retention, which is a key parameter, how successful education was. And I noticed that because I hired a lot of university graduates for R&D, and if they are even 1 year out of school, and I ask them something from the past, especially which needs some equation, they always say it rings a bell. Basically, they don't remember anything. And I was very surprised by that. And later on, I taught for 8-9 years at UBC, and I was astonished at the zero retention. And then I started thinking about it. Why is there such low retention compared to old school systems which had very high retention? And the main reason for that is students today don't reuse anything they learned in some other course. So you go and take a course in math, and then you take a course in physics, but the courses are not synchronized. The guy who teaches you physics, he doesn't know which math you took. So he cannot reuse what you just learned. Like at the Technion, the whole program was synchronized. Like when you learned Fourier transform in math, the next week the physics teacher used it, and 2 weeks later the engineering teacher used it. So everything got reinforced because there were no electives. The system here is very different. There is endless electives, And whenever you teach, somebody in the class never took this course, and they says, "Oh, can you explain this? I don't know what this is," right? So you cannot make progress because there's always something you say that somebody in the class doesn't know, because there are so many electives. So I think the current school system is, maybe it's nice to make it interesting for students, have lots of projects and things to make it interesting, but it's terrible in terms of what do they really remember once
But
they
it still
graduate.
produces amazing engineers,
Oh,
right?
no,
Somehow.
that's because, look, if people are very smart, even if they grew in a cave, they'll be amazing engineers. So, but the question is, A, what do you do with the rest who are not so driven that they'll know everything anyway? And B, even the amazing engineers would be even more amazing if they had a mastery of the fundamentals. Okay? So the part I don't understand, there used to be a school system which produced all the geniuses of the last century. Why change it? It was proven. People had very good retention of what they learned. They understood the fundamentals. I don't know who came up with the idea. You don't need all that. And it's mainly project-based. And you do things supposedly to make it interesting for the students. But if you're not interested, you shouldn't be there in first place.
And in Technion, is it still like
I don't know.
non-electives? Like
were
you?
I was doing research there, but I never.
Look, I'm talking what it was 60 years ago.
I see,
So I don't know what it is today. But when I was there 60 years ago, there were no electives except the last couple of years and very few electives. But the first 2 years, there was 0 electives. And then later on, there were some minimal electives. There were some old German professors who escaped from Germany before the war, and they made up the program like it was in Berlin. They actually wanted to teach in German, but there was a big fight and they had to teach in Hebrew because they didn't speak Hebrew. So, but anyway, they made a plan and the students weren't asked at all. Like the students had 0 say about anything at the Technion, and it turns out it was great because the students don't know what they need. And, we took lots of thermodynamics and all the engineers complained. We said, I was in electrical engineering. And they said, why do you need thermodynamics to be an electrical engineer? And of course, there was nobody to complain to.
Picture.
The point is that they understood what you need over your lifetime, not just what you need to pass the exam. So they put together a program which was heavy on fundamentals. And it was a very, very good program, which the more I distance from it, the more I appreciate it. That when you look back over your life, what you really want is the fundamentals, because the details change every few years. If they taught us vacuum tubes, later transistors came, later integrated circuits came. So it wasn't so important to learn the up-to-date stuff, because it changes anyway. What's important to learn the things which never change, like the fundamentals.
First thermodynamic law, second one.
No, so anyway, when I compare the experience of teaching till 10 years ago when I taught at UBC to the school system I went through, the biggest difference was retention. The students here have near 0 retention.
When you first came here, right? You came, I guess, like my parents came to America, you basically came with nothing, right? How did you get to like a checkpoint where really you had done something? What was your first thing that you did that was like a breakthrough for you professionally?
It's the same boring story you heard too often.
But just short,
No, I opened the yellow pages. There was no internet. Looking for electronics to find a job. There were 4 pages of electrolysis, which is, for ladies, to remove hair for ladies, and 4 lines of electronics. Okay, so I applied to the 4 companies listed. 2 were already out of business by the time they published the yellow pages. But anyway, finally I found MDA and I worked there. And I worked on image data processors for satellites, but then they needed a film recorder to record the satellite images. And not being biased by any prior experience, I told them I can build them a film recorder.
Like at that time, I understand electronics was like the prime
Yeah,
direction
but
to do research? Like if it's
electronics became software, and for some reason I didn't like software, so I had to switch. So I switched to optics, and I built them this film recorder. I built it at home, actually, because MDA was a software company. It didn't have machine shops or anything. So I built it at home, and it was very successful. Okay, for some a very successful product, which is used in all the satellite stations in the world, and later on used in other things.
What was the trick? Was there one major difference between what you did and what was out
At
there?
the time, there were no color lasers. At the time, there was a red laser, helium neon. There was no laser diodes, of course. There was a red laser. There was a complicated blue laser, but there was no green laser. So you couldn't make a color film recorder because you needed red, green, blue. There was no green laser. So I had this idea to take white light and run it through an acousto-optic modulator. An acousto-optic modulator is something which sets up a diffraction grating in a crystal by sending a compression wave from a piezo transducer. So basically you have a tunable diffraction grating. So you take white light and have a slit, just like a spectrometer, and you send in one frequency, you get one grating, and you get one color through the slit. You send in another frequency, you get a different grating, you get another color. So you can generate the colors from white light by changing the frequencies that you feed the acousto-optic modulator. And that was a breakthrough because now you can have a color recorder. All the recorders before that were black and white.
With AOMs, acousto-optical modulators, can you have that much change in frequency and wavelength?
Yeah, you can have a huge change. Because and you don't need a big change because if you have a slit, you just need to shift the color of spectrum a little bit to select a different color. It's just like in a spectrometer.
Oh, because I used to the ones which are maybe in megahertz range shifts or
but let's say you have a 10 megahertz drive, okay? And you give it 9 megahertz and 11 megahertz, so that's 10% change. So the whole beam angle changes 10%. Now 10% is enough to select the color.
No, we send let's say red light, and then the acousto-optics, it shifts by a tiny bit. It's not like
no. You send in
He's
white
sending
light.
white light and then splitting it.
So. Yeah, you get a spectrum.
Okay.
You send in white light, you get the color.
Okay, so you
spectrum.
make a dynamic grating.
Yeah, but exactly. But the cone with the spectrum can be tilted by changing the frequency.
So question, maybe we backing up, a film recorder, what do you do? Now you have a few colors of light. What does it mean to have a film recorder? What
you can make satellite images.
Is this a satellite? So there's a satellite that has a camera looking at the ground. What happens next?
Well, the satellite camera is multispectral. It sends down data in infrared, red, color, and you want the films, the pictures you study, you also want them multispectral. And the displays at the time didn't have enough resolution, so you can actually look at the data on a computer display. Because the satellite sending down stuff at 10K by 10K resolution, the displays at that time were 600 pixels by 600 pixels.
So you needed a way to put it onto a physical substrate.
Yes, so you have to put it down on film so you can see the little details. So there was a big need for film recorders. And the best thing is if you have a color film recorder, like the pictures you saw from Mars probe many, many years ago, that was done on this machine. That NASA sent it down and printed these pictures. The pictures which were on the cover of Time magazine.
So the film recorder actually is on Earth. You get the data from the satellite, and then you're basically generating.
Print big pictures, very high resolution.
Okay.
And then it was used for other things, for mapping, for many other applications. But the driving force was that the satellites started a bit before that. They sent out tons of data. There was no display device. You can look at the data because of the high resolution. So you needed a hard copy. And you actually looked at the hard copy with a loop looking for fine details.
So how does it work? Let's say in terms of collecting the data, let's say
then you store
Mars rover or
first you print a hard copy, but at the same time you also store the data digitally. So later on you can print some other pictures or process it.
So it was collected digitally.
It was, but what I built, the first machine I built was just a printer to print the films. later on, I also built a machine which was called an optical tape recorder, which was actually helped collect the data in a compact way optically. Because at that time, everybody believed that the future of data storage is optical, which was a mistake. But everybody believed in that. So did I. And somebody said that everybody tried to build an optical tape recorder and failed. And I said, great, that's an opportunity.
So this optical tape recorder, is it same as, like, let's say it's written like a CD,
yes.
But you write it on a tape?
Exactly the same. It's exactly a CD or DVD written on a tape.
Also those chalcogenide glasses, or what's the material was used for
it ablated little holes. Every bit was a little hole.
I see. Just the holes.
Yeah, a hole or a mark.
Okay.
Yeah, it was the same idea as DVD or CD on a tape, but the tape has a lot more area. So a reel of tape, like a CD was, say, less than a gigabyte, a tape was a terabyte, which at the time sounded astronomical amount of data, right? That was 40 years ago. Today is nothing. It's just this thumb drive, okay? But at the time was very exciting. But again, as I mentioned before, that magnetic recording had a breakthrough in the GMR, giant magnetoresistive heads, which basically increased the density orders of magnitude. So nobody needed optical. So it was an amazing achievement to build this machine, but there was no money in it. It's like the guy whose social insurance number matched the winning number in the lottery. It's amazing, but he got nothing.
But in terms of how long the data can be stored, is it still that holds the advantage compared to the
advantage was
drives?
archival. That's a good point, because magnetic data had some problems with the tape relaxation and then becoming brittle, and the optical was supposed to be archival. But in computers, you don't need archival because technology changes anyway every few years.
Just keep changing.
But the claim to fame was that this would be archival storage.
I'm curious. So you mentioned about the dilemma that, like, let's say 100 years ago, the tools were built to last forever.
Yes.
So now, with all these upgrades in software, like materials, so these tools become obsolete pretty soon.
Okay, what happens?
So don't we lose the precision because we're not make it to last for?
No, what happens actually? The tools are not thrown out because, like, these tools cost tens of millions, hundreds of millions.
Right.
So when it becomes obsolete, you don't throw it out. You move it to a company which does less than the most advanced chips. Because when you make computer chips, there are the CPUs and the memories. These are the highest density chips. But you still have gates, like AND gates, OR gates, gate arrays. Those don't need the nanometer line widths. So when a machine is obsolete, you move it over to produce lower grade chips. And then you sell it to East Europe to make even lower grade chips. Then you sell it to Africa. So basically, each machine of this expense isn't thrown out. It just gets degraded and to make lower and lower quality products. So the lifetime is not very short. Maybe it can reach a 15-year lifetime, but to make what it was intended to, it's a very short window, like maybe 5 years and it's obsolete. But it finds a use to make lesser chips.
But they still are designed to last for a long time.
Well, they're repairable.
With the best materials, it's not like a customer devices which are like 5 years you throw away.
No, because the consumer devices are not repairable.
Yes.
So when you buy some computer and the operating system is obsolete, you throw it out because it's not repairable.
Right.
But if you buy a machine which costs 400 million, you can upgrade and repair, and the supplier helps you upgrade and repair.
Do you think that there's, like, now just recently a lot of talk about, like, putting data centers in space?
Yeah.
Do you think putting lithography in space would help some way?
No.
You have the vacuum for free.
Not enough.
No benefit. Doesn't help with the parabolic shape, for example, right? Like, it doesn't help with the precision.
In my own mind, this whole idea of populating space is absolute nonsense. Because, people say we'll run out of space on Earth, we should design for life on Mars. To me, it's absolutely nonsense, because the the least hospital place on Earth, which is totally deserted, is still 1,000 times better than Mars in terms of, making life there. So,
but let's say you have free vacuum in space. Does that help?
But vacuum is cheap.
Yeah, vacuum
is
is
cheap.
cheap.
It's not a cost.
And no gravity also.
The cost to get there.
Like, can you get much better stage precision if you have no gravity, for example? Because then there's no warping from gravity.
Yeah, but you can compensate for gravity.
You need to design those stuff there because whatever has been done, like we have, the knowledge.
These are not practical ideas. I know that NASA is constantly looking for ideas why space is important. And they say, for example, if you are in space, you can make hollow balls for ball bearings. And actually, this has a huge advantage. If you can make ball bearings with hollow balls, they have 10x better performance because the balls will be elastic and not indent, not Grinnell. So there's always some list of things you can do in space which you can't do on Earth, which has an advantage. But when you compare that benefit to the cost invested in it, it's not very practical. The economist Keynes said about things like this, that if you feed the horse enough oats, some will ripple through for the sparrows. So there's always some side benefit, but it's not effective. It's not.
And gravity feels like you just make, let's say, rotate it, and then you can compensate the G.
You can have a rotating thing which cancels gravity, but you can also put a magnetic field which cancels gravity. Like this whole thing, if you want this to be in space, you put an electromagnet with a servo system which makes this float with no gravity. So there's such easier solutions than to cancel gravity than going to space.
Yeah, I think that for some very specific things like the fiber, I always forget how to pronounce this, but like a very low loss fiber, it needs to be drawn in like genuine zero gravity to be like extremely low loss. But these are like edge cases.
No, as I said, you can always find a couple of unique examples.
I think the way they make it is they fly an airplane, and then when they let it fall, you do these kinds of flights.
You have a zero G point.
Yeah, they do and they pull the fiber while the airplane's falling.
The other way, like this. At the top, you have zero G.
At
the top is zero G. That's how
the roller coaster,
That's how they train astronauts. Yes. But these are all marginal examples. But and there is always some other way to solve the problem. Put two fibers and lower the bit rate. There's always, the story with NASA when they went to some company to build a pen which can work in space, because a normal ballpoint pen doesn't work in space because it relies on gravity for the ink to flow. So they said, in the space you want to take notes. Anyway, the NASA paid $300,000 to develop a pen which you can buy. You can buy in museum stores. It's called NASA Space Pen, and it works in zero gravity. But then some guy said, why didn't they use a pencil? Which is true, because there's always a simpler solution for all these exotic things, like go to space to make some part. Anyway, I don't buy that. But they want to justify the billions spent, so they're looking for things like this.
You mentioned before that scientists like Maiman or others, so they were like great scientists, but on the entrepreneur side, they completely failed.
Yes.
And I think this is
very
common among the scientists.
Very common.
And what makes you unique that you combine these two features of entrepreneur and the scientist?
No, I don't. What makes me unique is that I understood that I would be hopeless in business. You see, which the fact you understand it is already a great step. Because most people who are good scientists and invent things assume automatically they'll also be good at business. Now, I have the advantage that I knew I'll never be good at business, and I always partner with people who are good in business.
How did you come to that realization?
It's very simple. My dad was a writer. So, where would I get the genes from for business?
Okay.
So you have to come by these genes somehow through your family tree. And, my dad never could make a cent. And my dad's main concern was that when I grew up, that I wouldn't develop any interest in the arts. so he wanted always to see me build stuff and go to engineering because life as a writer is hard life. So I understood that, I should always look for a partner to look at the business side. So that's the secret of being successful.
But how do you choose a partner then? Then you're just moving the problem to another space.
No. But, from business dealings, like at Creo, I had some partner, and then we met our customer who looked very, very good at business. And we asked him if he wants to come to work with us, become a partner with us. So through business dealings, you meet some people which impress you. Okay. And then, but the fact that you realize what you're good at and what you're not good at and shouldn't do, that's already a huge step towards success. Because a lot of people who start a company don't understand that they're not good at business. And they just don't have the mindset for business. Okay. The moment they understand that, they're already miles ahead of people who think they can do everything. Okay.
So what makes the person a great businessman? How do you see that? Okay, this person is
he always first has to think about economics the same way that I think about technology. You're looking for a business partner who constantly thinks about economics and money and everything. Because basically, I believe that if you don't think about something when you shower, you're not in the right field. because I can do many jobs, but I wouldn't be good at them. I would be passable at them. As I said, I was an infantry soldier at the Six-Day War. So obviously I could do other things than engineering, but the stuff that interests you is the stuff you think about at the shower. And that's the stuff you should pursue. Okay? Because then you have a chance to have ideas because your brain is working on it 24 hours a day, not just 8. Okay, so I never think about business when I shower. Okay, so clearly I can do it if I have to, but that's not where I will do great things. And the people who are good at business, they think about it when they shower. Okay, and that's what you're looking for.
I like this criteria.
Yeah, no, that's the best criteria. Okay, so anyway, I think it's important. You are right. It's not so trivial to locate a person who's good in business, but sometimes you meet one through dealings, through business dealings. Sometimes you meet one through recommendations, but that's a very critical decision,
But then would you see like among, I don't know if it take like maybe like famous person like Elon Musk, for example, is he more like a business person or he's more like as the engineering and technology side? Because it seems like he was also like reading a lot of
No, he's a business person. No, he's a business person, a very good one. But he understands technology, has a degree in physics, understands technology, but he didn't invent anything in technology. If you go and look at him, like Tesla, the car company, Elon Musk joined it when it was already making electric cars. Everybody said Musk started Tesla. He didn't.
No.
Company was started by two guys who were terrible at business. And they went bankrupt right away. And Elon Musk saved them. He invested some money and fired both of them. but the original Tesla, Elon Musk had nothing to do with it. He joined them where it existed already, the Tesla Roadster. But he understood the potential, the business potential, and he understood that the first step to great success is to fire the two founders, which he did right away. Okay, because he understood how hopeless they were, and then he made a great company out of it. But he's not a technical guy. He never invented anything, technology. And in other projects he does, he never invented anything.
I mean, he would probably argue that he's like pushing people in the right direction based on
absolutely. No, if you show him a good idea, he'll immediately grasp the potential of it and push it in the right direction. But, he didn't invent the idea, but he's very sharp to understand.
The thing he's probably the best at, I mean, obviously everyone's looking at, you're looking at it from a distance, but it seems to be recruiting, actually.
Oh, he's amazing.
He's a recruiting machine.
No, he's amazing at recruiting. He's even more amazing at raising money, because in the early years he had to raise a lot of money. He's amazingly brave and taking all his money and risking it on high-risk ideas. and making it succeed. He's an amazing fellow, but he's not an inventor of technology. He's a business person who understands technology and understands how to make it happen.
In that vein, actually, because he has like somewhat similar life story to yours in that he moved to Canada first. Why didn't you eventually, after having some success in Canada, go to California or like another hub in America to scale up or something?
I'm not an ambitious person. Okay. No, I'm serious, because my ambition in life was to have a lab like downstairs and enough money in the bank that during my lifetime I'll have enough money to play in the lab and never worry about money. Once I achieved that, I lost all ambition. Okay. So I don't consider myself an ambitious person, and certainly not in business. Okay. And the companies I started after that were for hobby, because you have to do something. I don't play golf, so what will I do all day? But it is not because of ambitions. I'm the opposite of Elon Musk, who was incredibly ambitious and incredibly driven.
Maybe you can touch on, you mentioned some of the companies that you started, more recently. So you've been actually working on some medical devices.
I was co-founder of 2 companies in medical devices. And as I said, one is very successful.
Can you show? You have the device, the prototype
one
here,
of them does this thing.
You kind of have to be near the microphone, otherwise.
One of the companies is called Cardium with a K. And they make this thing which folds into the catheter. So this whole thing folds. You push it through the leg into the atrium. It opens up in the atrium to this ball.
In the heart.
In the heart, in the atrium of the heart. And this ball has like a couple of hundreds of electrodes. And each electrode has a little heater, a little resistor behind it. So first you heat up all the little resistors, and you measure the cooling rate of the blood flow. So the more blood flow, the more cooling there is, the lower temperature.
So there are hundreds of wires connecting?
Yeah, hundreds of wires coming out here in a flat cable. So now you can map the whole blood flow in the atrium, so you know where the...
Is there a limitation on how many data?
No, the original version had even much more wires. Original version had hundreds more wires.
What's the thinnest wire you can do?
Oh, you can do very thin wires. It's not the wires are not the problem. You can make very thin wires. The problem is
but it doesn't have like resistance issues or shielding that.
No, you do it right. Okay. The challenge was to make this thing fold inside the catheter and unfold reliably.
Okay.
Because it's one thing. If it doesn't open up in the heart, it's not so bad. But if it opens up in the heart and doesn't close, then you're in trouble. Okay, you can't go home. Yeah. So to make...
How do you monitor the process of delivery?
At the beginning, you're under X-ray. So you can see it going to the heart, you can see it open up. And after that, you don't need the X-ray. Because once it opened, it maps the blood flow. So it knows where the mitral valve is. It knows where the blood comes in, comes out. It knows basically...
But it's just by having like a 3D map of the flow rates.
Yes, yeah. So the 3D map of the flow rates is a 3D map of the atrium. Because what you want is to know where the ports are. Okay, and then, hold on, and then each electrode also measures the electric potential. So when the heart pulses, there is currents going everywhere. And if the heart is working properly, the current from the pacing node ends up only where it should, and the ventricle contracts. But if there is a fibrillation, the current goes everywhere and things contract where they shouldn't. So this, at the same time, picks up the currents everywhere and shows you a 3D map of the currents. And then it decides where to ablate to kill the currents which shouldn't be there and just leave the right current. So you have to realize that the heart tissue is unlike any other tissue. The heart tissue is designed by nature to be an amplifier. And this is to guarantee the heart will be self-starting. So this tendency of the heart tissue to amplify means that if any current goes where it shouldn't, it gets amplified and cause big trouble. A normal muscle doesn't amplify. The current can cause it to shrink, but the tissue isn't an amplifier. The heart tissue amplifies everything. So once it sees all the voltages and the currents, it decides that this should be enclosed in a circle to isolate this erroneous current. So it shows the doctor, it's a suggestion, ablate here, ablate here. The doctor can edit it. Then he pushes a button and it ablates these circles around the sources.
How does it do the ablation? Just heating up?
No, it does it with a pulse which causes the cells to stop conducting, and that process is called irreversible electroporation, which is quite an interesting process. The original version was
It's
done...
like blowing holes in the cell membrane.
Yeah. The original version just did heating, RF heating. The new version does electroporation, which doesn't heat, just makes holes, as you said, in the cell membrane, and the cells stop conducting. But when it finishes, it does one more thing. It pulses a pulse and checks if now everything works. So before you take it out, you can do a self-test. So it pulses at the center and sees the electric field propagate, and it sees it in multiple points in parallel, which is very nice, because when the pulse propagates, all these sensors pick it up and show you a wave map, a 3D wave map, to make sure that the procedure was successful.
But how can it pulse? I understand it's not touching the walls of the
No, it's
heart.
close enough. It doesn't have to touch well, because the current will go to the wall.
Just through the salt water, just through the blood.
Yeah. And usually it's touching close enough that the pulse will start, and even if it doesn't touch to pick up, it will pick up most of it. So the blood.
Do you have to ground the person then?
Yeah, the person is grounded. Yeah,
Okay.
and you can anyway. So it picks up all the currents, draws a 3D map to show that it was successful, the ablation, and then you fold it and take it out. Okay. And the amazing story that a friend of mine who was a co-founder of Cardium, his name was Amos Michelson. Cardium was founded by 3 guys, and I'm one of the 3. And the second guy was a businessman, and the third guy was a cardiac surgeon. So Amos Michelson was a businessman behind Cardium. Halfway through the road of Cardium, developing the road, he got fibrillation, severe fibrillation. So he waited until his development was finished. And 2 months ago, he was treated with this device and got rid of his fibrillation.
Amazing.
So it paid back for him. The investment in Cardium paid off because he got treated with the device he helped develop.
How long did it take? So Cardium is now on the market.
Yes.
How long did it take to get it to the market?
Forever. Almost 20 years.
20 years.
Almost 20
20 years.
Yeah. Because we started with a different approach with the RF ablation, and then we switched to irreversible poration.
What went wrong with RF?
Oh, it's not wrong. This was better.
Okay.
There was nothing wrong with RF. It was actually approved in Europe and used successfully in Europe.
Okay.
But the poration was better. And one reason the electroporation was better, it didn't rely on intimate contact. Even with a bit of blood gap, it still works. So the whole road from concept, beginning, till now being used in the US and hopefully going public, this whole process is almost 20 years, which is a very long time.
So what's your take on, because nowadays, like investors or in general, like people want to see like fast returns.
Not in medical, they understand it. The people who invest in medical are not the people who invest in Bitcoin or AI. It's a different mentality. They understand it'll take years, and they understand there could be big payback if the device is really good. But it's probably...
How much did it cost to bring it to market? Was the total like
funds? $500 million. Roughly, round numbers. Okay. It's a huge amount. I never expected at the beginning that it will take this kind of money to bring it to the market.
One of the problems where you thought it's going to be like easier, but then turned out to be
that's exactly one of the problems. That when I looked at it, I thought it'll be like 10 years and maybe 100 million, and it was almost 20 years and 500 million. Yeah, exactly one of these problems that I underestimated. It's true.
How much were you involved in the fundraising? Did you have to put a lot of effort defending the technology?
I put a bit of my own money. Amos Michelson put a lot of his own money. Okay. And that was a good sign for the investors that will believe in it, and then they put in the heavy money. Yeah. But, it's a long road. Medical is a long road, but you do get the satisfaction that somebody you see them use it, and they get healthier, and it does have... See, most of the products which people make, nobody needs, actually. You know, you make another gadget, a more advanced iPhone. Nobody needs it, right? So you have the satisfaction that you made money, but deep down you know the people who use it will be just as happy without it. But if you do something in medical, it's different. You see people use it and it helps their life, helps their health. So even if you're not altruistic, just the fact that you see the difference it makes in people's life, that's actually a nice feeling. I don't have a particular interest in medical. The fact is I didn't continue in medical. But I have to say that you do see how it changed somebody's life, while in other fields, it's harder to see that because, you know, you make a slightly better car, a slightly better cell phone. It didn't really change anybody's life.
What's a fundamental kind of like problem that's labile to technology? So not like, you know, a philosophical problem, but maybe a problem that hasn't been solved that you don't necessarily have an idea how to solve it, but you think it would be amazing to solve it. Like, I don't know, flying cars, whatever. What's like a kind of dream problem that you haven't solved yet?
I think, you know, there are areas which are crowded, which means a lot of people are working on it, and your chance of coming up with an idea there is not very high because all these smart people are working on it. But there are areas which are totally neglected, which have the same impact. And the chances of coming up with an idea in an area like this is much better because the bright people somehow don't go there, and the potential is just as big. So, for example, I mentioned before material science. To me, an area which is full of unsolved problems and untold riches is material science. Because I mentioned before that no material which was ever invented became obsolete. Okay? Like we still use pottery with a 10,000-year-old process. We use laser tanning, which is a 20,000-year-old process. We use metal extraction from ore, which is a 5,000-year-old process. You know, we use glass. Basically, every major process which was invented 1,000 years ago is still in use today. Some materials, the importance went down a lot, but they didn't become obsolete. Like, for example, the first polymer invented, which was significant commercially, was bakelite, phenolic.
Yeah,
it's still used today, but it's not easy to injection mold, so you see a lot of other plastics used. But it's still used in critical application today. So
where's bakelite still used?
Bakelite is the best plastic for electrical appliances because it doesn't soften when it's hot. The reason why all these things you buy from China melt and burn and break down is they're made from molded thermoplastic. So as soon as there is some markings, they get hot.
Was bakelite machined? Or
no, bakelite is thermoset. It's cross-linked.
I see. Okay.
So bakelite, because it's cross-linked, is much stronger, and it's particularly good for temperature, high temperature. So if you have a socket or an outlet, everything used to be bakelite. So if it got a bit warm, it didn't melt all over and short. Today, everything is plastic, thermoplastic, and it's troublesome. But anyway, like the important stuff is still bakelite. But I'm saying that some materials which were very important, bakelite was the most important polymer 100 years ago. Now it's a niche, but it's still used quite a lot. So there is no end of potential in material science, and nobody's working on it.
So what materials are we missing?
For example, there is a material called liquid metal. The company has the same name, liquid metal. And this is a material as strong as steel, more flexible than steel, astonishing material, and can be molded like plastic at 400 degrees. It's basically the ideal metal. You can mold it like plastic, so it comes out perfect and cheap. It's super strong, super elastic, has everything you ever wanted from a dream metal, but it's fragile. If you drop it on the floor, it breaks like glass. Now, there is no fundamental reason it has to be fragile. It's a metallic alloy. If somebody can take out the fragility from liquid metal, it changes the world. Because everything which is done by machining today can be done by molding.
What's it made of?
It's a zirconium alloy. The main component is zirconium, and then it has a couple of other metals. It's if you look up their website, Liquid Metal, it's an astonishing astonishing selection of properties.
So I think working backwards, like let's say what is constrained today by materials? Like you gave an example, you have to machine metal.
Yeah.
Which is an expensive process,
Yes.
and then machine part, if you want to get an injection mold, you have to machine the mold. Takes weeks.
Yeah, but if you can have metal,
but if you can mold metal, then it's easier.
Mold metal, which is properties of steel. You can mold zinc, you can mold aluminum alloys, but they don't have the properties of steel.
Right.
But if you can mold metal to get properties of steel or better than steel, that changes the world.
Okay.
The reason both Apple and some other company bought a license to Liquid Metal because it will allow them to make computer cases and smartphone cases which are paper thin and strong and don't dent. But you can't use it because it's brittle. That's just an example. So material science is full of examples of kind of unfinished work that if somebody can solve any one of these problems, it changes the world.
Yeah, I guess the issue is that it's very unpredictable. It's hard to set out. It's not like a mechanical system or something where you can think through it.
Very true.
It's very hard to set out and solve. Like let's say you take this tap. Yes. You can imagine this tap in your head. I don't know if you can imagine.
No, that's very
of course, you can think through like the crystal structure and have like guesses and
but you're right. But it's very unpredictable, especially in material science. A lot of things defy logic.
Mm-hmm.
The steel we use now for all cutting tools is called high-speed steel. And you have seen the name high-speed steel, I'm sure, on cutting. This is the best steel for cutting tools. Everything in the world for cutting tools is made of it. It was known in history that when you harden steel, you shouldn't overheat it. Because if you overheat it, it burns the carbon, so it wouldn't harden. And it was also known that to harden it, you have to cool it rapidly, like quench it in water. And there was one guy by the name of Mouchet in England, and he overheated a piece of steel. He was experimenting with steel, and he overheated it. And he realized it's ruined because it became, instead of red hot, it was white hot. And then he threw it out because there was no point in quenching it because it was overheated. It was already useless. And the next day he came back to work and he saw this piece of steel on the floor. But being the curious type, he picked it up just to see what happened. And he realized it's harder than any steel he's ever made. And that was high-speed steel.
Is it like carbon migrates from the inside or something?
No, it has a strange property that some carbon is burned off, but there's still enough carbon in it. And it is the only steel which actually does not have to be quenched. It hardens just by cooling in air. And it's the only steel which has to be overheated to get hard. So basically he did the two things which everybody knew will ruin steel. And the combination of the two created the best steel in the world.
So we need to make more mistakes.
Well, Teflon was invented like that, right? Same story. It was Planquette with Teflon, right?
Graphene, same story.
But Teflon, he had some gas which polymerized inside the bottle. And he was throwing out the bottle, but he said, he already threw it out. He picked it up again and said, it's strange what did the gas polymerize into. It was a fluoride-based gas, so he peeled off this white layer from the inside of the walls, and he said, let's dissolve it and do some analysis. And he couldn't find any solvent in the whole lab which could dissolve it. And then he realized he created a polymer which no solvent can attack. That was Teflon. Okay, so material science is full of stories like this. And you're right, it's very unpredictable. If you set out to invent this material, who knows? But that is an area which was neglected for many years and full of surprises. Okay, but what can be done? Because there is no limit fundamentally there is an infinite number of combinations of things. And some materials, it's the same material, but you just heat treat it differently and it becomes a different material, right?
So could it be that, we can build like a robot setup which would try to all different experiments?
That's exactly what they do. Very much like an assay in biology.
Yep.
They just have an assay and a robot tests everything. And that's how a lot of material science is done because there's just too many combinations. And you use exactly this kind of methods. But I think the problem is that the bright people are not exposed to this field.
Yeah, it sounds like a boring field.
If you're in high school, people want to work in AI, want to work in robots, want to go to space. I never heard anybody in high school who said, I want to be a material scientist, right? So that's exactly the problem.
Yeah, I studied material. That's what I did at Technion, for example, for 2 years. I think like the issue with materials is that if you want to do, the problem is this, I would say, this is my opinion. Big companies are no longer a good place to work. Like there are very few big companies where it's fun to work. Like nobody wants to work at IBM or something like that. Like most people don't, right? If you're like ambitious and smart. Maybe like Google Labs or something, but they don't work on this.
By the way, they all hate it. I worked with Google a bit. I have friends there. It's an astonishing story because Google treats people better than anybody on earth. Benefits and salaries, they all hate it.
They're not happy, yeah.
Do you know what is the average stay for a Google employee?
No.
It's 16 months or something.
Okay.
Wow.
It's one of the places with the highest turnover in the US.
They get recruited out because Google selects very good people. Isn't great at keeping them, and then they get recruited out.
But the other guy doesn't pay them more. Why would you leave if you were treated well?
Right.
Anyway, I had a long discussion with Google people because I couldn't understand. Nobody could be treated better.
What don't they like?
Pardon?
Yeah, what don't they like?
Bureaucracy. They have to go through much bureaucracy. All kinds of things.
Well, basically, if you build something there, the chances it gets launched are very low. So you're just working on things to put them on the shelf. I think that's my outside.
That's true. That's what I heard. But also everything has to be approved, bureaucracy, and I don't know what.
Anyway, so there's not like a Bell Labs where you can go and like have your Bell Labs. Maybe now with the AI labs like Anthropic or something. But if you want to work on physical stuff, there's not like a Bell Labs for that.
You're right.
So then your options are academia, which has a lot of issues, right?
Yes.
Not everybody can survive there like psychologically.
No, it's terrible. Bureaucracy is even worse.
Yeah, exactly. And then and it's also zero sum. There's only one seat, let's say, for something at Harvard, and everybody's trying for that seat.
Yeah.
So that's academia, and then you're left with startups, right?
Yeah. And that's what's happening.
And the problem with startups and materials is that, again, materials are so unpredictable that basically, what's your pitch? It's we're going to sit down and just start doing stuff, right? Like there's not like a
you are 100% correct.
Very difficult business plan to say like we're going. But now actually people are raising money. I mean, on and off to use AI to discover materials.
Yes.
I don't know to what degree there's really something there.
I don't know.
But at least it's the minimum threshold that it passes is that it's fundable. Because it gives investors the idea maybe there's like a trick here. You found a trick. You have AI, so like we'll give you some money to try it out.
You describe it 100% correct. Because I spent time in academia. I wasn't subject to the bureaucracy because I didn't get paid. I just taught for fun, so I didn't have to go to meetings I didn't like because they couldn't fire me. So basically, I saw the best side of academia because I didn't have to deal with the bureaucracy. My youngest son was a professor at UBC in AI, and he quit the week he got tenure to start a STEM high school. But he couldn't wait to quit. He just waited for the tenure so he can quit, because somebody told him if he quits before that, people say he didn't get tenure. That's why he left. So he had to wait. The moment he had tenure, he resigned. But the bureaucracy drove him crazy because he's a very efficient fellow, and it just drove him crazy that, especially at UBC. But what my surprise was that I always blamed it on UBC because it's a state university. They have to thank the natives every day. They have to do all kinds of things. Anyway, I thought it's their fault. And then I worked with MIT. I told you about this video. And I worked with Alex Slocum. And he wanted to build a prototyping center. And I said, I'll send you videos and I'll send you what you need, because I built the same setup you see downstairs. I built 6 of those in Vancouver.
Really?
Yeah, two for the university, 1 for the cancer agency. Amazing. So I built a copy of that many places in Vancouver, so I knew exactly where to buy. And everything.
What's the cost of that setup?
$1 million. But I have a fancier one you need. Most people don't need a jig borer, don't need metrology. Most people, they need $500,000.
Okay.
But anyway, so I talked to Alex Slocum and said, I'll make you videos if you need help with selecting equipment. I love this stuff. And he said, great. And I made him the videos. And then I asked him a month later, so how is it coming? He said, we need to make a 3-foot wall where the machine goes. We need to add the extension of the wall 3 feet so we can put the machine. So I'm waiting for the builders to come. And then 6 months later, I call them and say, well, is it running? No, we need to build this 6. 2 years later, they still didn't manage to get this piece of wall. And that's a private university, nothing to do with unions, just with bureaucracy. Because, I blamed everything here on unions and government, but apparently in a private university, it's the same.
So where does the bureaucracy originate? Like what is a big problem in general?
Well, probably at MIT it's different in different departments. Who knows?
Yeah, maybe.
But the size of the organization.
It's all about the motivations involved.
Yeah, right? It's to line up the incentives. Yeah. In a university, it's hard to line up the incentives. That's a problem.
No, but there used to be, like, for example, MIT's problem is not that it's part of the government. It's that MIT is considered like number one. Yeah. And if you're number one, sometimes that hurts you. Because, like, for example, when they started University of Chicago, originally when they started it, Chicago was kind of a startup. Like they had an inferiority complex.
That's
and
good.
So they were collecting Nobel Prize winners from wherever they could and like cutting all the red tape for them, buying them whatever they wanted, that kind of thing, because they needed to build up like a good university. And that helped. They did make a good university at Chicago through that kind of effort.
You remember when Avis started, when the car rental company Avis started, their motto was, we are number 2, so we try harder.
Yeah.
A very good motto.
Who was the number 1?
Hertz. Yeah. And they came in the second car rental company in the US. They became very successful. They had a very clever CEO. Okay, but that was their motto for many years.
No, but there is an aspect of that probably just because it's so well regarded that like there's room to be incompetent. There's like it's a certain kind of like empire complacence type of thing.
To me, the guy who explained bureaucracy the best was a German general by the name of Kurt von Hammerstein. I don't know if you know much about Kurt von Hammerstein. He was a very interesting fellow. And he was at some point the head of the school of German officers. He did serve under Hitler, but he was against Hitler and actually tried to kill Hitler. He was an anti-Nazi. And he died during the war from cancer. But anyway, when he was running the officer school in Germany, he explained that all the German soldiers are a combination of 4 properties: stupidity and cleverness, laziness and industriousness. And he says, the ones who are clever and industrious obviously are a great blessing. We should retain them and blah, blah, blah. The ones who are clever and lazy are actually surprisingly useful because they come up with shortcuts because they're clever and lazy.
Yeah.
And he said, the ones who are lazy and stupid, he said, let's face it, that's the core of the German army. We can't do without them. Every army, most of the soldiers are lazy and stupid. Without them, you cannot have an army. But the ones who are stupid and industrious should be expelled immediately because they're the ones who make all bureaucracy. That is very, very sharp observation, because the most dangerous person to get into an organization is somebody who's stupid and industrious, because they sit and make rules and make complications.
Well, what do you think of the humanoid robots? What's your take on humanoid robots?
That is a very serious business which will change the world, because it's on the verge of doable. And once you do it, basically it will change the world, because all the jobs which can be done by sitting at a desk will be done by AI. Because if you sit at a desk, read a report, send emails, AI in a few years can do it for you.
Yeah.
A lawyer, radiologist, accountant, AI will do it. Even driving cars and all this. Now, all the jobs which you can do from your desk, where you really have to stand in a factory floor or do in a field, in theory, a humanoid robot can do for you, right? So, and it's going there. It's going there, and it will change the world completely.
Fully replaced.
No, so you think, so what will we do? What will we do?
Yes.
If the jobs a person has to do not at his desk will be done by a humanoid robot, at his desk will be done by AI, so what will we do?
Podcasts?
Yeah. No, it's going to be a big shift in the world, but it will happen because the payback is huge.
Yeah, I think one thing that people talk about is that like the hand is very difficult. That
it's
actually
very
the human
difficult.
hand is like, turns out to be, a lot of people talk about this, like, and anyone who comes from that space.
But it was very difficult to get to the moon, and there was much less benefit in it than making a humanoid robot. There's a huge prize there, a huge incentive.
Okay, this is actually a good question to you. Is how do you run so you've had some engineering teams that you put together for your companies.
Yes.
What's your approach for managing an engineering team?
So my approach is to look for people who are obsessed with technology, because the ones I hired were the R&D types. I didn't hire the managers; somebody else hired them. But so the ones I was really interested in are the types who would come up with new ideas, R&D types. So usually, I would look at their grades, test them, but also I would ask them what's their 5-year plan, okay? And say the ones who said, I want to do R&D, and where do you see yourself in 5 years? I think in 5 years, I see myself in management. I'd never hired. Because I said, why don't you go to management right away if that's where you want to end up? Okay?
But that's a traditional path, like in all big companies.
I know,
but
the ones who are true technical guys never see themselves in management. They say, I want to have a lab and do this. And what's your plan in 5 years? To have a bigger lab and do more things.
Yeah.
Because they're totally obsessed with one thing, with technology. So first of all, you ask a question, where do you see yourself in 5 years? And everybody who says a manager is out. Because obviously he's not obsessed with technology. Okay, and then I ask him, what do you do for hobby, to see if they have any technology-related hobby. And most people, when I ask them, do you have any hobbies? They say, yes, we ski and yodel and swim and bike. And I say,
we have a podcast hobby. I'm meeting with people like you.
No, because anybody who lists me 10 hobbies, I said, this guy has no time left to read about technology. So he's out. Okay. Because I like the guys who say, he's looking for a job as an electrical engineer. And what's your hobby? I come home, I build more electrical things. That's the type of guy I'm looking for. But if you put together a team like this, you find like 10 people who are obsessed with technology, you can do amazing things. And if you run it non-bureaucratically, because several times in my life, I went into the field, which we were a startup, and we competed with the biggest companies in the world in this field, and we won. Like, like I mentioned this optical tape recorder, which big companies like RCA and Philips failed. Okay, and we succeeded, again, with a 10-people team. Or Cardium, with a team which had no medical background. That was the ex-Creo team. When we sold Creo to Kodak, some of the people left, and we took the best team, and we made this team to do medical. 0 medical background. In 10 years or 20 years, they have the best product in the world for ablation. Okay, so if you have a difficult problem, you want to have a small team, so you don't waste time managing the team. You want to have a small team of obsessed people. Okay. And all the ones who ask how many holidays do you get here a year, out. I read a funny story that I read a book about Sam Altman, with OpenAI. The guy says that he came to some company he was interviewed with some company, and there was some guys there. He asks the interviewer, do you have to work on weekends here? Okay. The interviewer said, well, we try to avoid it, but sometimes there is no choice, there are deadlines, so yes, we have to work on weekends. And the applicant says, great, I just wanted to know if you're a serious company. Otherwise, I'm not joining. So if you want to develop technology, you have to have obsessed people. Okay? And so that makes a world of difference, because if they think about it, if they're interested, they think about it 24 hours a day instead of 8. Okay? And they talk about it, and so that's a secret. And then you give them freedom and let them make mistakes. I mean, don't come down on them if they made a mistake. Wasted some money. That doesn't matter. Because the main thing is there should be obsessed people who really like what they're doing and think about it all the time. So yeah, so if you have this team, you can take on problems that big companies failed because they don't have the motivations. They have bureaucracies, and people are not motivated and leave, turnover, all kinds of problems with big companies.
Mm-hmm.
And my biggest surprise was talking to these guys at Google, because I was astonished how many of them want to quit, although they have infinite budget, good salaries, free food, free transportation. Every benefit you can imagine is theirs, and they're treated well and everything. They're not happy.
Yeah, maybe it turns around now because finally Google is like in danger, so they're getting more serious.
And they did a huge progress with their AI.
So because they're like now they're in genuine. It's more fun to be in the game
maybe,
now. They weren't really playing the game.
But if you have a small group which is kind of threatened because they compete with bigger companies, you can do a lot of things. Because one of my first projects was a company which did the first good mobile data terminal. If you go in a FedEx vehicle, they have a mobile terminal, they can scan when they pick up, and they can, it all synchronized with the computers in Memphis. So we developed, the company was called MDI, and we developed for FedEx these mobile terminals, which at the time worked through the mobile radio in the car. Okay? And the competing company was Motorola, which bought us at the end. And Motorola was a huge company, dominated mobile radio, dominated everything. And we decided to compete with them to make a mobile terminal better than their terminal. And we did.
What was the reason you chose that problem?
Oh, the Canadian government wanted a mobile terminal, and they gave us some paper study at MDA, which was painfully boring. And I didn't feel, I had some part in this paper study, but it was really painful. So, but nobody really knew what I was doing, so I decided to develop a modem, which is much better than the existing modems, because I had some telecom background. So I managed to develop a modem, which was much better than the existing modem, and I convinced MDA to develop the whole terminal, not just the modem. And then they had to convince the Canadian government that that's okay, because originally Canadian General Electric was supposed to develop. So anyway, we got eventually the contract taken away from General Electric. We developed the terminal, and this was the first product in the world which used the Reed-Solomon error correcting code. And the Reed-Solomon error correcting code is a perfect code to correct errors in mobile communication. And that was...
How does it work?
Pardon?
How does it work?
Do you know how in general error correcting codes work? Yeah. So the Reed-Solomon code, in every code, theoretically, if you add n bits, you can correct n over 2 errors. That's a theoretical limit to a code. But it's very difficult to make such a code, because the theoretical limit is known, but to actually design a code which can correct n over 2 errors by adding only n bits is very difficult. And Reed-Solomon code was the first code where it was easy to implement and reach the theoretical limit. And when you deal with mobile transmissions, there is bursts of errors. It's not just 1 or 2 errors. You can lose like 1,000 bits at a time, because the FM radio you work over has fades. Fades is like dead spots where the RF signal drops to 0. So you have a chopped up signal where you lose thousands of bits at a time. So with the error correcting code before Reed-Solomon, the theoretical limit was known, but nobody could implement a code to do that with the computing power of those days. And the Reed-Solomon code had a relatively simple implementation which could run on a microprocessor. Okay? So we made this terminal. It had a novel modem, which ran 2 to 3 times faster than any other modem, and it had the Reed-Solomon code, which worked many times better than any other correcting code. So it became a very good terminal, and so FedEx decided to rely on us rather than Motorola. That was a big break. But 2 years later, Motorola bought the company. That was the end of the story.
Well,
but I mean, that was also like a small group of people going against the leaders in the field. And I had this experience many, many times in my life. That if you have like 10 good people, sometimes even just 5 good people, and funding, of course, which is another story, you can take on very, very ambitious things.
Could you project it, let's say, if we come back to academics, university, like usually there's like research group of students who are typically motivated and can work days and nights and think about it in the shower to have that.
Some of the students are, but I have many professor friends. They don't work on research. They work on filling out papers, writing grant applications.
Right.
They just waste all their time on things which are not research.
But maybe for someone like you, for example, where you don't may need to bring the grants, for instance.
Yeah, that's what
and like focus more on solving the problem with the students.
So first you have to get yourself in a position where you don't have any distractions except focusing on solving the problem.
That's right.
Yeah. And for that, you need about $10 million because you need $1 million to build a lab and $9 million, so nobody can fire you.
Just to give aside to university.
Put aside, and and so you have to do something to collect $10 million. Any startup will do that if it succeeds. And after that, you can really concentrate on research.
That's what I'm thinking. What you're gonna do, while
no, that is the right plan.
I
think that is the right plan. Because once you don't rely on grants, you don't rely on investors, you have your own lab, you can walk down, do stuff whenever you want. It's a totally different life.
Absolutely.
And you don't have to ask anybody, I want to buy this machine. You don't have to go to your boss, explain to him why you need this machine. You just pick up the phone. Okay. So to really be an independent scientist, you need $10 million, which sounds like a lot, but it's really not a lot. Because, one good startup, no matter even if you have a small part of it, you get your $10 million.
Okay. But is anyone doing this right now? I think it could be a good new...
You're saying
for universities, like people, let's say, who, I don't know.
Show up to university with their own funding.
University with their own funding and do focus fully on research problems.
Yeah, but eventually you get tired of them and then you want... For some reason, like your wife needs to move to another city, so you have to move to another city, and you're not independent. You're still kind of, and there is bureaucracy in every university, and then you say something politically incorrect, and you get into trouble. So there's always distractions. University, at least judging by my friends, and I have friends in US universities as well, it's not that you focus on research all day. You spend a lot of times in meetings, you spend a lot of times helping students with applications, you write reference letters, you fill endless forms. The percentage of time you're really in your lab thinking and solving a problem is not that high.
Absolutely.
So your output isn't that high. And in Canada right now, only 1 grant application out of 8 is approved. I don't know the ratio in the US. So these friends of mine here who write...
10%.
10%, same, same. So basically I have this friend who's a very good professor and with many achievements. He's writing this grant and he knows 90% chance he'll be rejected. So what fun is that? You write and write and write, and then he gets back a letter that it didn't cover the native people aspect or something, and it's rejected. It's terrible. It really feels miserable. Because it's like communism. This guy happens to be from Romania. So he still remembers communism. Okay, he says it's just like it was in Romania. so that's a frustrating part.
I mean, I guess the issue partially is that it's a little bit universities, let's say 100 years ago, weren't as industrialized. There were just fewer people interested in being professors. It wasn't as common to want to be in that position. So it was more like it was just less crowded, right? Because people would really do it just because they were like extremely passionate about it.
And in other countries, like in Germany, you have something in between university and industry.
Like research centers?
Research centers. So you can work in a...
Are the outcomes better in those centers?
Yes, okay, because less bureaucracy, more budget, and stability. You don't have to guess, will I get the grant renewed or not? You have stability.
Same was in Russia, actually.
Yeah, so like the Fraunhofer Institute in Germany, you're accepted to work there, you get a budget, you get a salary, you don't have to look for grants every year, and you deal with industry, you work on practical problems, and the results are pretty good. So there is in other countries a different solution to that problem.
and you separate like people who want to do research. You don't push them to teach.
Yeah,
because usually they're like, I need to teach the course.
And
but
some
then
people like
who are
to teach.
passionate about it, they
I
would
know.
fully.
Anyway, I don't have that much experience with university because I only taught at one place, but I have many friends in many universities, and they all don't look so happy because they really don't do what they like to do. It's research. And the more senior they are, the less they get to do the things they like to do. The more they're tied up in things which are wasting time. Like this friend of mine in university in Chicago, she says the thing which drives her crazy, she has to pass, and she's in biology. She has to pass an ethics test every year online. Maybe you have too if you're in university.
No.
So once a year she has to go online, sign into the ethics test. And before the ethics test, there is a quote about the importance of ethics. It says, ethics is a foundation of everything we do, blah, blah, blah. And the quote is from the guy who is now in jail for selling Obama's seat to somebody else in the US. So he was arrested, but they didn't update. He's still, the ethics test starts with a quote from him, and everybody knows he's in jail. So basically, it's frustrating, you know. So basically, between you and absolute academic freedom is $10 million. And it sounds like a lot, and I know you're young people, and you say, where will I get $10 million? But one startup puts you there, and then for the rest of your life, you are a free man, you can do 100% of the time research, and the life is great. Okay.
And that's what happened to you, right? So you don't have to deal with all this kind of noisy things, but focus on
it didn't happen by fluke. That was my plan all the years. My plan was to get to Canada, get a job, start a company, get the $10 million. At that time, it was less than 10 million, and then do what I want. So I had this plan from a young age. It just took several years to get there. But that was always my plan, that to get to the point where I have a lab and enough in the bank that nobody can fire me and I never have to worry.
So what's your next big challenge?
Well, I'm getting old, you know. That's different. Now it's just hobby stuff. Okay. I have this company for
making the trains.
Yeah, that's in between when I think about what's the next challenge. You know. But I'm getting older, so it's less important.
Let's say you were 40 today, right?
Yeah,
and you could work on any technical problem. What would you work on? If you had like a 20-year window and lots of funding to crack it.
I don't know, because if I really knew clearly, maybe I would start working on it now.
Materials?
No, maybe not materials. Maybe, I don't know, something in the field of energy, maybe. I don't know in what field. It has to be something you are truly interested in. So biology is very important, but I'm not truly interested in. Medical is very important, but I'm not truly interested in. So, would have to be something, electricity, mechatronics, metrology.
Dan, it was amazing talking to you. Thank you so much.
Very inspiring conversation.
Is there anything that we didn't cover that you wanted to talk about?
No. Maybe I'll show you this graph, or I send you by email this graph of this, how the inventions peaked in one area.
Please.
Because that's a thought-provoking graph.
Can you describe it?
Well, that's basically of the 100 most important inventions in the world, most of them were crowded into a 60, 70-year space. And then it decayed, the rate of inventiveness decayed. So most of the important things in the world were invented between 1850 and 1920. And if you take the list is not something I made up, the list is all the list on the internet that other people made up. So you take all the list of the internet of 100 most important inventions, average them, you get a list which is what everybody agrees on, and then you plot the year versus the number of inventions, and you realize it was crowded in a very narrow space of time, and then the discussion why.
That isn't it. Do you have a hypothesis?
Well, it's a complicated story, but I'll send you the graph, and then you think about it, because it's a thought-provoking thing. What should we change to come back to such a period of inventiveness? Right?
Dan, it was amazing talking to you. Thank you so much.
Very inspiring conversation.